Okay, good people. We're now embarking on a really fascinating topic, and that's called the rank of a matrix and its relation to systems of linear equations. Now, we've done systems of linear equations many times in this class and before you got to this class, but we're going to see some new insights based on this, um, useful insights based on this concept of rank. But before we can get to rank, we have to talk about something else, and that's talking about something called a row space and a column space. And basically, a row space means like this. You have a matrix, okay, and the matrix has rows and has columns. Well, imagine I would take these rows, take the individual rows. See the top row, A11, A12, A1n, and just write that as a vector. And then take A21, A22, A2n, and we're writing that as a separate vector. We're kind of dismantling this matrix and writing it into a whole bunch of separate vectors, um, kind of like a chop shop. And similarly, so these are called the row vectors of the matrix A. Um, now, the span of these row vectors is going to be this thing called a row space, because we know that if you take any set of vectors and you take their span, it will form a row space. It will form a vector space. We've established that already. It'll form a subspace of the of the larger vector space. Similarly, we could do the same with the columns. Here's my column A11, A21, AM1, and we get column vectors. Column vectors. So we have, look at the column vectors. The first one is A11, A21, AM1, A12, A22, and so on and so forth. So here we have a bunch of row vectors. Here we have a bunch of column vectors. Now, it may not be the same amount because this is an n by m matrix. There are n by n matrix. There are m rows here and there are n columns here. So the amount of rows, the amount of columns are not, necessarily the same. That's fine. I'm just saying. So let's look at an example. Let's say A is a 2 by 3 matrix, meaning 2 rows, 3 columns. So the row vectors are 1, 0, 1, -1, because I just took off the top row. And the second row vector is -2, 3, 4, which is basically the bottom row. The column vectors are 0, -2, 1, 3, and -1, 4. Because again, I just took the 3 columns. So notice that there are 2 row vectors. So my row space is coming from these two. My row space eventually is going to come from these 2 row vectors, and my column space is going to come from these 3 columns. There's only 2 of these, but as you can see, they're longer. There's 3 of these, but they're shorter, which means that the row vectors and the column vectors are really from 2 different worlds, because the row vectors are from the world of R3. The column vectors, as you can see, are from the world of R2. So row vectors and column vectors are kind of 2 different worlds, yet we're going to see a tremendous connection between them, a tremendous connection. I just want to point out one more thing. No one is saying that these 3 vectors here are linearly independent. They may be, they may not be. We're not saying anything about that. We're going to get into that very soon, but we're not making any guarantees of anything right now. We're just taking these 3 vectors, which may be independent, may be dependent, and we're going to span them, get all the linear combinations, and that is going to eventually form some subspace of in this case it'll be a subspace of R2. The truth is, I could tell by looking at this that these 3 cannot be linearly independent. That's because I know the rest. That's because I know what's coming up in this section. But and as soon as you learn it, you're going to be able to just look at these and know that these 3 cannot possibly be independent. Anyway, let's get some official definitions here. So the row space and the column space of a matrix. So you have A is an m by n matrix. The row space is a subspace of Rn spanned by the row vectors of A. And the column space of A is a subspace of Rm, M like Mike, spanned by the column vectors of A. And that is what a row space is. That's what a column space is. Now, okay. So here's a really important theorem, and a useful theorem. It's going to help us. We're going to use it a lot. Row equivalent matrices have the same row space. Meaning, if I take a matrix, and I do my elementary matrix operations to get some row equivalent matrix, those two matrices will have the same row space. And the proof is kind of proof in the pudding. The proof is kind of it's common sensey. So let's just go through it. So you started with matrix A, and you're doing a bunch of operations to get matrix B. So the rows of B were obtained from the rows of A by elementary row operations, scalar multiplication and addition. By the way, there's another elementary operation, which is switching rows. But switching rows is kind of irrelevant here. If we're talking about a bunch of vectors, the order that you have vectors in doesn't matter. I mean, I'm not saying switching rows is not significant. It definitely affects the determinant, affects a whole bunch of things. But for this particular specific thing that we're doing, the switching rows won't have much of an impact when we're talking about the span of a bunch of vectors. So let's just look at scalar multiplication and addition. Well, guess what? Scalar multiplication and addition, that's linear combinations. That's what linear combinations are. So basically, the row vectors of B can be written as linear combinations of the row vectors of A. That's what this is saying. And which means that the row vectors of B lie in the row space of A. I'm not saying that the row vectors of B is exactly the same as A, but we know that since every row of B came from linear combinations of A, so B is at least included in the span of A. That's what we're saying, which means it's included in the row space of A. And the subspace spanned by the row vectors of, now similarly, the subspace spanned by the row vectors of B is contained in the row space of A. Because if the vectors of B lie in the row space of A, the span of the vectors B is going to lie within the row space of A, because that's what row space is. It's just every possible linear combination in the world, just combine. Now, on the flip side, we know that the rows of A can be obtained from the rows of B, also by elementary row operations, because you just do the reverse operations. We've done this in previous. So A is contained in B, B is contained in A. The two row spaces are subspaces of each other. Well, the only way that's ever going to happen is if they're equal. The only way I'm a subspace of you and you're a subspace of me, it's only going to happen if we're the same thing. So we see that you're going to get different vectors, but the row space of A and the row space of B is going to be different. Now, matrix B, now here's a really super duper important theorem. If a matrix A is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. Let's get a sense of why that's true. You know, when you do elementary row operations, you try to get rows to like zero out, get rows become entirely zero. Basically, you're doing everything you can to turn rows into zero. But there are some rows that were impossible to turn into zero. Well, if it was impossible to turn those rows into zero, it must be that they were linearly independent of all the other rows. So the non-zero rows are like sort of the survivors, and then they survived because they were linearly independent of the other rows. So the non-zero rows are all going to be linearly independent. Now, which means they're going to form a basis for the row space of A. Which means that if you have 5 rows, and you get the bottom two rows become 0, and there's only 3 rows left in the matrix in this row reduced matrix, then that means that the dimension of the row space would be 3, not 5. Actually, we're going to see a very specific example of that. That's actually coming right. I gave away more than I should have, because that's coming up right now. So we want to find a basis for this row, for the row space of A. So row space of A, oops, here we go. We want to find a basis for the row space of this matrix A. And it is notice there are 5 rows and 4 columns of this matrix A, and we're going to find a row space. So the first thing you want to do is put it into row reduced form. And I have the steps right here. So here's row reduced form. So this is where A started. I just copied what you saw on the screen a second ago. So I did a bunch of operations. 3R1 plus R3 becomes the new R3. In other words, what am I doing? I'm doing my standard thing. The standard thing, we're coming in like the Terminator. We're using the 1 here to get rid of the -3, get rid of the +3, get rid of the to the 2. We basically want to clear out. We want to clear out that that first row. So the first thing we did is 3R1 plus R3 becomes the new R3, and now my R3 looks like this. Now I want to get rid of the 4th and the 5th row. These two, I want to get rid of the 3 and I want to get rid of the 2. So -3R1 plus R4 becomes the new R4. -2R1 plus R5 becomes the new R5. The truth is, I could have done this step and this. I could have done all 3 steps at the same time, because they're kind of independent of each other. You got to be careful when you do multiple steps at a time. You got to be careful, because sometimes when you do one step, it affects. You just got to be careful that it doesn't mess you up. But in this case, these are all like independent of each other. Anyway, now what's happening, I got all zeros down here. So the third row is 0, 9, 9, 8, -5, -5, -8, and the bottom row is -6, -6, -8. Now I am going to do 3 things at once. I want to get rid of all these numbers and turn these all into zeros. So all the numbers beneath this leading 1, I want to turn into zeros. So I'm going to add -9 time. I'm going to take row 2, add -9 of row 2 to row 3, add +5 of and negative and +6 of row 2 to row 5. These are the steps right here. And when I do that, I get a big bang for my buck here, because not only did I zero out everything here in the second column, but I zeroed out everything in the third column. And now I'm going to I'm doing my steps, step by step, and I'm turning this 8 into a 1, because I want my leading, ones. And so 1/8 of R3 becomes the new R3. And now it's child's play. I'm just going to add 8 R3s onto these bottom 2 guys and completely zero them out. So if you notice, I got the bottom 2 rows are all zeros, and it's just the top 3 rows. So 1, 3, 1, 3, 0, 1, 1, 0, 0, 0, 0, 1. These are the 3 rows, and these are linearly independent. And yay! So that means the basis of the row space, these form a basis of the row space. These 3 are linearly independent, and the basis of the row space consists of 3 vectors, which means it's a 3-dimensional row space. Now back to where we were. So here we go. So as you can see, they did the same thing here. They went 1, 3, 1, 3, 0, 1, 0, 1, 1, 0, 0, 0, 0, 1, and they got the same results. Why did I bother doing it all by hand? There are all these calculators and softwares and things where you could, my feeling is that when you do these by hand, you just get more of an insight. Now, I'm not giving you a matrix. There are matrices that, which could be like, literally like 1,000 rows and 1,000 columns. And of course, I'm not giving you something crazy like that. But these matrices, when you do it by hand, when you do all this stuff by hand, you just get a little more of an insight, a little more of a feel for what's going on. I can't encourage that enough. In fact, on the tests, I require it. On the tests, I require you to show me, by hand, all the operations by hand. Um, anyway, these three guys here now are form the basis for the and that's what we're saying on the bottom. Form the basis of the row space of A. So yay. Okay, let's move on and let's find the basis for the now this technique here. I just want to point out this technique that we just used to find the row space of to find the basis of a row space. We could use this to find the basis of just a bunch of random vectors, because what we do is, let's say we have three vectors: -1, 2, 5, 3, 0, 3, and 5, 1, 8, and we want to find the basis. So obviously, if I take the span of these three vectors, it becomes a subspace of R3. Now there are three vectors here. It could become the entire R3, or it might just become a subspace of R3. It really depends on how much it spans. Anyway, well, you'll see what I mean. Anyway, so we take these three vectors, we do a bunch of operations. I'm not going to go through the operations this time. I'll let you do it by hand, and we get this right here. So notice that there are two non-zero rows and one row zeroed out, which means that of these three vectors, they're not independent. They're dependent, and however, I have two rows. I have two guys here which are independent. So therefore, the basis of this set of the basis of the span of the span of S of the subspace, which is spanned by S. That basis is 1, -2, -5. That's my first row over here, and 0, 1, 3, which is my first row over here. And voila, which means that this subspace is only two-dimensional, not three-dimensional. But hey, that's showbiz.